have a great video for you today, so let's jump straight in. Here is the circuit we're going to analyse. As always, no number crunching or formula slinging, just intuition for observation to start with. I've given the real values of each component so you can try this yourself. Please don't forget physics is supposed to be tangible. The layout looks strangely familiar. It's that of a potential divider with a capacitor where R2 would normally be. Could that give us a clue to its operation? I bet it does. Our input is a signal generator producing a sine wave as well as we will be analysing the AC behaviour. I'm going to slowly sweep up from hertz into kilohertz and then into megahertz. We have two oscilloscope probes attached to the circuit, yellow on the input and blue on the output as always. Let's look at the function and intuitively analyse it at each stage. Firstly, we can observe both waveforms have the same frequency and amplitude. Although they look the same amplitude, please remember that no potential divider will output exactly the same input. There is always a little loss, but on the whole, not much of interest to see yet. Now if we crank up the frequency, say 100 Hz steps, you can see the frequency counter top right of the scope. Now as we increase the frequency, the output amplitude is decreasing. Now we're in the kilohertz. Let's play devil's advocate and go right into the megahertz. Now the output is pretty much non-existent. So that's really interesting behaviour. At low frequencies the output is pretty much the same as the input, but at high frequencies the circuit blocks the input. Now let's run that sweep again and consider the approximate equivalent circuits to help us understand what's happening. So for low frequency, in the hertz, the capacitor acts like an open circuit. Its resistance is incredibly large, effectively trying to output the input. As we move into the mid-frequencies, the kilohertz, we begin to see the amplitude decrease, almost like a conventional potential divider, where the resistance of R2 is dropping. This resistive quality in the capacitor that is dependent on frequencies is known as reactance. The higher the frequency, the less reactive it becomes. When we get into the megahertz, the capacitor is almost acting like a short circuit due to its reactance being very small, where the output is almost being shorted to ground. So what do we have? From our experiments and looking at a combined approximate equivalent circuits, we have a passive low-pass filter. This filter lets low frequencies pass but blocks high frequencies. If we plot this response of amplitude versus frequency, we get the following. The point where the amplitude starts decreasing is known as the break frequency, with formula 1 over 2 pi RC and is considered to be at minus 3 dB. This reactive quality of the capacitor is often called impedance. However, there is slightly more to it, hence why I've called our circuits equivalent and approximate. If we compare the waveforms again, but expand our time base, at the base frequency, we can also observe a phase shift in the output of approximately 45 degrees. Therefore, impedance is a combination of reactance and phase shift. The phase shift requires complex algebra and is not in the scope of this video, but rarely is cause of concern. In reality, the phase shift and amplitude are interlinked, and you cannot specify them independently. Due to our simplification, our circuits are actually an abstraction of the physics, not completely analytical, but will work well intuitively. In this video, we have learned about the low-pass filter. We have seen its construction and analysed its output intuitively, creating approximately equivalent circuits to aid understanding when the input is driven by different frequencies, and can understand impedance. Now take a look at this transistor driving circuit. Can you recognise the low-pass filter? Without even needing to write a single formula or understand the complete function of this circuit, we can understand that for some reason the designer has used a low-pass filter to block high frequencies from the input. I hope you enjoyed this video. Please give it a big thumbs up. Now stop watching YouTube and go and build a low-pass filter to impress your friends. By all means, start with my values, but it's more fun if you try your own. If you can't build this circuit at home, maybe you don't have an oscilloscope or a sine wave generator, why not simulate it instead? I have a bonus video about free software simulator LTSpice linked below, taking you through the steps. Until next time, keep experimenting.